They outsmarted us again. That's the verdict from scientists who've just learned a brand new trick from Earth's tiniest master pilots. And it may flip the way our robots see the world. Welcome back to Dynamic Trends, where we scout tomorrow's tech sometimes in the most unexpected places. Today's unlikely teacher, the Apis mellifera, better known as the honeybee. Researchers at the University of Sheffield have shown that a bee's aerial dance isn't random. Each bank, roll, and zigzag programs its brain to read visual scenes faster and with less computing power than many super chips at sheffield.ac.uk. In plain English, motion becomes computation, and if we can copy that, autonomous drones, self-driving cars, even AR glasses could get sharper eyes with slimmer batteries. So grab your field notebook. We're diving into 5 chapters. What bees actually see in flight. Busting the big brain equals big smarts myth. Plugging bee logic into AI chips. Robo-insects that could save our crops. Where bio-inspired vision goes next. A worker bee's brain about the size of a sesame. It houses under 1 million neurons. Compare that with our 86 billion. Yet in flight it can filter clutter, separate flower from foliage in milliseconds, gauge depth by sweeping left-right. It feels how images slide on the retina, turning motion parallax into a 3D ruler. Recall landmarks, a 3 kilometers homing trip with the family of 50,000 waiting for dinner. The Sheffield team built a neuromorphic modular digital emulation of the bee brain and fed it video captured on a robotic bee cam that copied natural zigzag maneuvers. When the model moved like a bee, recognition accuracy of complex pattern stripes, spots, even human faces shot up by 40%, all while using a fraction of the energy a conventional CNN needs. For decades, engineers assumed smarter meant more layers, more silicon, more watts. But experimental neuroecologists, led by Professor Lars Chicker, ran the numbers differently. By silencing select neuron groups, they found bees need only a few dozen Kenyan cells in the mushroom bodies to tell a flower's chevron from its bullseye. That flips the old IQ scale on its head. Think of it like code golf for biology. The shortest, cleanest algorithm wins. If a bee accomplishes landmark recognition with kilobytes, why does your quadcopter burn through a laptop GPU just to avoid a tree? The lesson: trim the fat, borrow nature's shortcuts like lateral inhibition and sparse coding, and your hardware suddenly lasts all afternoon. Enter the Active Vision Stack software that pairs each microsecond of the camera with instant rewiring of the perception model. Early trials on indoor nano drones cut inference latency by half and slashed RAM needs by 70%, all thanks to those Sheffield equations. But why stop at drones? Self-driving cars grapple with edge cases every sunset. Imagine LiDAR that wiggles micro mirrors just enough to mimic bee-scan paths, grabbing extra depth without spinning an entire roof rack. AR glasses could flick tiny MEMS mirrors to sharpen object contours only where your gaze lands, saving battery and bandwidth. Over at MIT, researchers shrunk those principles into a paperclip weight flyer. Thanks to flapping wing thrusters and elastic joints, it can hover, pitch roll yaw, then pull a double back flip all while packing an onboard vision chip smaller than a grain of rice. Why care? Because global pollinator decline threatens up to Philippine peso $600 billion of crops annually. Picture multi-level urban farms where 100 robo-bees zip through tomato vines, each tagging blossoms with electrostatic pollen puffs. Early greenhouse trials showed up to 20% yield bumps with zero pesticide drift. And because their brains are bee-inspired, the bots adapt, avoiding overlapping flight paths and learning blossom colors in real time, not just GPS waypoints. The result? Higher coverage, lower energy, and fewer mechanical crashes compared with traditional quad rotors. We're entering the age of frugal intelligence. Instead of brute forcing every pixel, tomorrow's machines will move to make the problem easier, just like bees. Expect 3 waves: edge AI accelerators with bio-inspired scanning kernels, shipping in wearables by 2027. swarm robots for agriculture, and search and rescue that choreograph their sensor motions to map debris fields without GPS. Adaptive optics in satellite images, subtly wobbling mirrors to beat atmospheric blur at a fraction of current power budgets. Yet the biggest payoff may be philosophical. The Sheffield study reminds us intelligence isn't about gigaflops. It's about the right flops at the right moment. Nature beat us to that optimization 100 million years ago. Our job is to take notes and maybe, just maybe, keep up. So, what do you think? Will bio-inspired vision overtake deep learning megamodels? Could a swarm of robo-bees rescue the almond harvest? Drop your thoughts below. The hive mind is open. If you learned something buzzing brilliant today, smash that subscribe and hit the bell so you never miss our next deep dive. And for the full list of papers and a behind-the-scenes look at this episode, check the description. Until next time, keep your eyes moving and your mind active. If you enjoyed this video and want to stay ahead of the curve with the latest breakthroughs in science, tech, and innovation, make sure to subscribe to Dynamic Trends and hit that notification bell. And don't forget to check the link in the description for 10 amazing Amazon products inspired by today's topic. You won't want to miss them.